Okay, we'll start with going over the solutions for exam 2. So the first question was to find the shortest path tree using Dijkstra's algorithm. So you're given this graph to start with, so you will initialize the estimate of the shortest path weight from A to A as 0, from A to every other vertex as infinity, right? So now you start with the vertex with the minimum of this estimate weights, which is 0. So from A you are trying to see if you can reach its neighbors, right, basically. So you're going to check if the weight of this path from A to B of weight 0 plus 5 is going to be less than infinity, and answer is yes. So we can reduce this from infinity to 5 and make this as a predecessor edge. Similarly, 0 plus 4 is 4 less than infinity, so we can change this to 4. Similarly, this edge from 0 plus 3 is 3. So then so we are done with A. So now we have to pick the minimum of these estimates of the shortest path weights 3, 4, 5. So the minimum is 3. So when you pick up an vertex, it means that we have optimized the path to that vertex. So that's the shortest path. So we cannot find anything less than 3 as the weight of the path from A to D. That is what it means. So from 3 to 7, it is what? 10. So 10 is less than 4? No. So we just keep whatever we have so far, right? So that's the only edge you have from D. So we are done with D. So now look at the minimum of these weights. It is 4. So which means you have found the shortest path from A to E. So now look at this edge. If you go to this edge, it's going to be 4 plus 2 is 6. Is 6 less than 5? No. So we'll just keep it what we know. Then 4 plus 3 is 7. 7 less than infinity, so we can change this to 7 and highlight this edge. So those are the only two edges leading from E. So we're done with E. So we pick the minimum of B, C, and F. The minimum is going to be 5, which means you have found the shortest path to 5, or the minimum weight path to 5. B. And so the edge leading from B, so this edge from B to F is of weight 4. So 5 plus 4 is 9. Is 9 less than 7? No. If this were a 1 here, 5 plus 1 would have been 6, and we could have removed the highlight on this edge and make this as a predecessor edge. But this is so 4, so 5 plus 4 is 9, less than 7? No. So we just keep with what we know. 5 plus 2 is 7, so we can reduce this to 7 and highlight this edge. So we are done with B, so only thing left is 7 and 7, so we can break the time by choosing the vertex with the lowest alphabet, so C. And this edge is of weight 1, so 7 plus 1 is 8 and is not less than 7, so we just leave it as it is. So we're done with all the iterations. So once we're done with C, F is the only vertex left. It's optimized by itself. So when you put together all these dark edges, this is our shortest path tree starting from A. Alright? Alright, so the second question was to show using a simple example that the heap generated using top down and bottom up could be different. So as I said in class, just consider a list of 1, 2, 3 and try to form a heap of this list. So if you use a bottom up approach, the heap would be just to first draw the binary tree. So if you draw this as a binary tree, it's going to be 1, 2 and 3, and you check now the leaf nodes. The leaf nodes meet the heap requirements. Now check the intermediate node. Is 1 greater than its 2 children? No. So swap 1 with the largest of those 2 children, which is 3. So 3 goes above and 1 comes here. So that's a heap you get out of bottom up approach. From a top down approach means you just construct the heap step by step. So with 1, this is a heap on it by itself. Then 1 to 2, so you swap because the root is lower than its children, so 2 becomes a root, and so this is a heap. Now 3 gets attached here. This is not a heap because the root is not greater than its 2 children, so 3 becomes the root, and then 2 comes here. So you get 3, 1, 2, different from 3 to 1 here, so the two heaps are structurally not the same. Okay. Okay, so let's look at this question. So you're given two keys, K1 and K2. We want to prove that in a binary search tree that has these two keys, if you do an in-order traversal of this binary search tree, K1 will be always listed ahead of K2. Okay, since K1 is less than K2, the theorem is K1 will be always listed ahead of K2 on a in-order traversal list of this binary search tree. So you want to prove this theorem. So the way we prove this theorem is, we are given that k1 is less than k2. So this k1 and k2 could be related two ways. Either they need not be a direct ancestor descendant, which means, by what I mean by ancestor descendant is something like this: k1 is kind of an intermediate node or even the root, and k2 is directly kind of on a path from k1 to k2, from the intermediate node to k2, or parent node to k2. That's what it means, right? So this symbol indicates there could be one or more intermediate nodes from k1 to k2, but still k1 is the parent and k2 or ancestor, and k2 is a descendant. Similarly, k2 could be the ancestor and k1 could be the descendant. Okay. Now, when I say they are not ancestor descendants, so they are kind of, there is one common node, say k3, which is the ancestor for both of them. So they are not directly like this, ancestor descendants. There's one common node k3 like this. Okay, so these are the two ways or three possible ways a binary search tree could be. So now let's see in each of them. So since k1 is less than k2 and there has to be a common ancestor connecting them, this k3 has to be greater than or equal to k1 and less than or equal to k2. Right? So if you do an in-order traversal of this binary search tree, you will visit k3 first, but you won't list it right away because you visit the left subtree first. So you go and visit the left subtree. So you will end up listing k1 first, and then you go to the root, list k3, and then, so that's what I show here, k1 listed first, and then k3, and then you list k2. Right? Similarly, if you have k1 and k2 like this, since k1 is again less than k2, when you do an in-order traversal of this, you will first go to the left subtree for all something's over there, and then visit the root, so you list k1, and then followed by the right subtree, so k2. So k1 is still ahead of k2. Similarly, if k2 is like this, since k1 is less than k2, the tree has to be like this. It cannot be like k2 is the parent node and k1 is to the right of k2. k1 cannot be to the right of k2 because k1 is less than k2 and it's a binary search tree. So the parent node has to be less than or equal to its right children and greater than or equal to its left children. So k2 has to be greater than or equal to its left children, right? So k1 is in the left, so k2 has to be greater than or equal to its left children. And since k1 is less than k2, this is how they could be related. So now when you do an in-order traversal of this, you visit the root first, but you don't list the root right away. You go to the left subtree and you list k1, and then you go to the root and list k2. Okay, so still k1 is listed ahead of k2. Right, so this theorem goes ahead and kind of proves the general one that we discussed in class, that if you have a binary search tree and you do an in-order traversal on it, you will get a sorted list of the keys. Right? Okay, so now we want to compute this 7 raised to 45 mod 13. So the way we do that is we write this 45, the exponent, in binary. So that's going to be in exponents of 2, 1, 2, 4, 8, 16, 32. So we write this in binary. So 32 is a 1, and then if 16 is a 1, it becomes 48. So you have to stay within 45. So this is to be 8. So 32 plus 8 is 40, 1, 44, and then 45. So we'll find the exponents of 7 from 7 raised to 1 mod 13, 7 raised to 2 mod 13, all the way to 7 raised to 32. So 7 raised to 1 mod 13 is going to be 7, raised to 1 is 7, so 7 mod 13 is 7. There's no multiplication done here, right? Then 7 raised to 2 mod 13 is 7 raised to 1 times 7 raised to 1, so 7 times 7 is 49 mod 13, which is 10, because it's 39 and the remainder is 10. Then 7 to the 4 mod 13 is 7 squared times 7 squared mod 13, so it's 10 times 10 mod 13, which is 9. 7 to the 8 mod 13 is 7 to the 4 times 7 to the 4 mod 13, which is 9 times 9 mod 13, which is 81 mod 13, which is 3. 7 to the 16 mod 13 is 7 to the 8 mod 13 times 7 to the 8 mod 13, which is 3 times 3 mod 13, which is 9. 7 to the 32 mod 13 is 7 to the 16 mod times 7 to the 16 mod 13, so 7 to the 16 is 9, so 9 times 9 mod 13 is again 3. So now we'll put everything together. So 7 raised to 45 mod 13 is 7 raised to 32 times, just looking at the binary representation of 45, so wherever there's a 1 you put all those exponents. So 7 raised to 32 times 7 raised to 8 times 7 raised to 4 times 7 raised to 1, the whole thing mod 13. So 7 raised to 32 was 3, 7 raised to 8 was 3, 7 raised to 4 is 9, 7 raised to 1 is 7, all the thing mod 13. So now 3 times 3 is 9, and 9 mod 13 is going to be still 9, so we'll stay with that 9, and then that 9 times this 9 is going to be 81 times 7, so 81 mod 13 is going to be 3, then 3 times 7 is 21 mod 13, which is 8, right? So the number of multiplications we have done here is going to be 1 multiplication, 2, 3, 4, 5 multiplications. So to find those exponents, why again 5 multiplications? If you see here, for this least significant bit, for this one we don't need any multiplication, for everything else we need 1 multiplication. So it is 5 multiplications here and 3 multiplications here. Alright, so again the number of multiplications we do here to put everything together will be again 1 less than the number of ones you have here in general. So that's going to be 5 plus 3 multiplications, which is 8 multiplications. If you did a brute force approach of this using your calculator, tapping 7 raised to 45 or 13, if at all your calculator can find it, it's going to do 44 multiplications, 1 less than the exponent value, because for example if you want to compute 7 to the 3, it is going to be 7 times 7 times 7, so you're doing 2 multiplications to find 7 to the 3. Similarly, you find 7 raised to 45, you will do 44 multiplications, which is far more than this approach, binary what is that, modular exponentiation approach, which requires only 8 multiplications. Alright, so now let's look at this binary search tree. We want to, given this sorted list of keys, we want to draw a binary search tree of this list of keys. So the way we do that is take up the whole range first. So we have from 0 to 8, that's the index. So from 0 to 8, the middle index is going to be 0 plus 8 over 2. Right, so the middle index is going to be the floor of 0 plus 8 over 2, so that's going to be what? 0 plus 8 is 8 over 2 is 4, so this 30 is the root of your binary search tree. So now to the left of the 30, everything will